Hello, everyone. Everyone online and everyone face-to-face. First time we've done it dual mode, and it's been fun so far, trying to make that happen. And for those who are watching in the future, hello, I'm David. It's summer semester 2021, and this is a revision seminar for Maths 1B. And what I'm going to do is share my document camera. And this is what everyone has said they want to talk about today. And I won't be able to cover it all, but I'm going to start with the multivariable chain rule and see what I can get out of that. Okay. Okay. So, let me formulate my thoughts on that. So multivariable calculus has lots of different ways of thinking about it. And the one that I find most helpful for the chain rule is to think that when you have a multivariable function, and it might be something like f of x, y, and z, or something like that. What that means is that you have several variables and they cause a result which is a number. And because changing any of these numbers changes the results, there's derivatives in several different directions. And so one way of thinking about multivariable functions is to think that, I am going to call this W, is to think that there's a value of x which lives on some sort of axis, and there's a value of y which lives on some sort of axis, and there's a value of z which lives on some sort of axis. And together these three produce a value of w which lives on some sort of axis. And as you change the input answers for x, y, and z, that'll change the answer for w. So maybe as x moves forward, this moves forward. Maybe as y moves forward, this moves backwards. Maybe as z moves forward, this moves forward faster than it does for x. Each of these numbers moving will cause this result to move. That's how I think about it, in this context anyway. Right. So you can think of x, y, and z as positions in space, and the w could be like the temperature, and that's one way of thinking, that these tell you the different coordinates in space, but it could also just be things that change. It could be parameters like, you know, the w could be the current population that has a certain disease, and this could be the current temperature, and this could be the number of people who have it now, and this could be, you know, some measure of, you know, useful social distancing, and as those things change, it'll change this. Oh, this is time. Like, doesn't really matter. There are lots of different things. So if you keep two of them the same and move one of them, that's called a partial derivative. Cool. Right. So if you move all three of them, then it's going to cause this to move in combination. The amount that this causes it to move, the amount this causes it to move, the amount this causes this to move will add up. So what I'm going to do is I'm just going to draw that, is that this could be a little change in x, and this could be a little change in y. I'm going to put it forwards. And this could be a little change in z. And the change in x is going to cause the w to move this way. The change in y might cause the w to move this way. And the change in z might cause the w to move this way. And all of this together is how much the w changes by. And the assumption in calculus is that if you make small changes, then you can just add up the individual pieces and that will be the result. Okay, cool. So in my head, it goes that how much W changes by will be a change because of X plus a change because of Y plus a change because of Z. So they're going to be, that's the thinking that's in my head. Okay, and this might not be how it's written because this is very much like doing an integration by substitution where I'm allowed to write dW all by itself. And the way calculus works is you assume that any change that happens because X changes is a multiple of how much X changes. So we end up with something times how much X changes plus something times how much Y changes plus something times how much Z changes. And the name of this thing is dW on dx. Curly dW on dx and curly dW on dy and curly dW on dz. That's what this is. This is how quickly W changes when X changes. So if I move X forward by a teeny tiny bit, I would expect W to move forward by this times that bit. And the reason we have to put this here is that this will be different depending on where X is. Because it might be that for different X's, if X is higher, that W will move faster than when X is lower. So this is why the multivariable chain rule, because this is the idea. Because if I suddenly went, well, what if I wanted to, what if the thing that was causing these three things to change was time? Because that's usually what causes things to change, is time. So I could imagine that how much dW changes with respect to time will be dividing both sides of the equation by the amount that time changes. And we now have a version of the multivariable chain rule. Right. If I'd had a day to plan this, I might have gone down a different route, and I'll probably go down that different route in a moment. But what I want to do now is to say to people, how are you feeling? And do you have anything to say? Yes?
Can I just ask, I can't remember why you have to use the curly Ds. What's the difference between curly Ds and straight Ds?
So what is the difference between curly Ds and straight Ds? That's what we've got from the room. And in the chat we have, why is it DW instead of DF? Okay, so why is it DW instead of DF? It could have been DF, and that would have been okay. It's just that the notation is really confusing. Function notation, like f of something, belongs more easily to this Leibniz notation, the d thing on d thing, whereas function notation goes better with the f little subscript x. And because I was wanting to talk about changes in an outcome, I wanted to talk about a quantity that was changing rather than the name of a function. Can I answer Josh's thing first, unless that was related to that? So why is it straight D and curly D? Okay, so we've got all people in the chat answering the question for us, and we saw that it's a straight D when it's dependent on exactly one variable, and it's a curly D when you have to choose among the several variables one of them. So the straight D is, in my head, the straight D is something that all by itself could represent a very small change in a quantity. D stands for difference. So a very small difference in W can sit all by itself, but curly dw and curly dx can't ever be separated. Well, I say that, but apparently in later mathematics they can. But for the moment, I've never seen that maths, so I'm going to pretend it's not there. Dw on dx can't, curly dw and curly dx can't be separated. They're joined together forever. And this thing is a thing all by itself, which says how much w changes just when x changes. And the curly is when you're choosing one thing out of many. So when there's only one variable to use, then curly dw on curly dt is the same as straight dw on straight dt. And because there's only one to choose from. But once you get to multiple variables, that's when they start to be different. Yeah. So you need the curly there to remind you yourself and everybody that there's more than one thing to choose from. And to remind yourself that this quantity is a thing by itself. Right.
Are you able to write that formula in that subscript XX or
I can give it a go. So, just give me a moment. So just for those, I don't know if you guys heard it, but Fraser asked, can we write this in the subscript FXX form? I'm presuming that we could write, we're going to still have to write df on dt, unfortunately, because we don't have a function name for the t, but this would be fx dx on dt plus fy dy on dt plus fz dz on dt. Because w is f of these things. We are allowed to be sloppy with this, like these brackets are here to remind us what this f is a function of. So as long as they're straight up things and there's nothing else in these spots, we can think of w as the same thing as f, and it would be okay to write curly f on curly t, curly t. All right, I'm going to step in a different direction now. So this picture here, I can think of these things moving, causing this to move. But I can draw this red arrow part of it a bit more schematically and think that w is a function of x and y and z. And I was thinking that x was a function of t, like that. Right. Okay. This is a picture of the original thing I said, and then I'm saying that these are caused to change by time. And the way I use the schematic to draw the thing is that dw on dt would be following every path that gets to t, and every arrow is a derivative. So this arrow would be dw on dx, this arrow would be dx on dt, this would be w on dy, this would be dy on dt, this would be dw on dz, and this would be dz on dt. And so dw on dt would be multiply down the branches, dw on dx times dx on dt. dw on dy times dy on dt plus dw on dz times dz on dt. So it's a schematic that helps me keep track of what's going on, but this is saying that when t moves, this is how much I need to multiply the change in t by to figure out how much x changes by, and then I need to multiply that by this to figure out how much w changes by, but I've got to keep into track of all three of the variables, so I need to add them together. And this schematic is useful for me because when I write Patrick, I have seen the question. I'll get back to it in a second. when I have X, Y, and Z aren't just being caused to change by time, they're being caused to change by something else as well, where there's more than one variable to change the X and the Y and the Z too, then I can draw another complicated diagram. What if the X and Y and Z were also changed by two variables? And then I could go, well, what's dW on D? So right down the bottom, U and T cause W to change, ultimately, but they do it via X, Y, and Z. So if I want to do dW on du, there's two choices for a variable down the bottom, so there's going to be a curly. And then I can follow every branch that gets down to u. So it'll be dW on dx, dx on du, plus dW on dy, dy on du, plus dW on dz, dz on du. And so that's these three branches. Yeah, right. Yeah. So that's my understanding of the multivariable chain rule. And if Z actually wasn't a function of U and it was only a function of T, then this branch wouldn't be here. So I'd need an example probably. Yeah.
Because there's two variables linked to X, Y, and Z, that's where you can go brackets and not the straight brackets.
Correct. So the reason why these aren't straight Ds is because all of these U's and T's were a choice of two options. Is that what you were saying? Yes, and that is the reason. Okay. So, and you can do that as many layers deep as you like. And there can be, it can be that W is a function of both X and Y is a function of X, and it'll be fine. So I could have something like and so I could ask at this stage, what is dW on dx? And I could just sub this in here and that would be fine. But I could also do it partial, like multivariable calculus wise. I could think that W is a function of X and Y is a function of X as well. And so I could say that dW on dx, because there's only one variable down the bottom, is dW on dx, the curly one, choosing the two variables, plus dW on dy on dx. So I could do that if I wanted. Yeah. So let's just see, dW on dx is 2x plus 2y, keeping the y's as constant. Yep. And dW on dy is 2x, and dy on dx is 15x to the 4. And so that means that dW on dx would be 2x plus 2y plus 2x times 15x to the 4. And if you really wanted to, you could sub in the y if you wanted. Right. That's a times there. No, I can't do it. I was going to leave it, but I can't. I have to finish it. Right. Okay. So you could do it that way. It would probably be quicker to actually just sub in the y in there and just do it straight. But I just wanted to show you that it's possible. Yeah. Patrick, does that actually answer your question ultimately? For w, x, y, z, what does dw on dx mean? It means how quickly the w changes when the x changes, but not the y and the z. That's the question that we were asked there. What would that look like? Back here, that would look like keeping these in the same spot and moving this and seeing how quickly this moves. You guys can see the chat, that's kind of nice. It's hard to know what it would, what the chain rule equation. Oh, the chain rule equation would just be this. Oh, and it would just be dw on dx is dw on dx. And that's it, because that's all there is. I really want to say there isn't any more, but that's just a reference to Madeline. Yeah, that's all there is. So I do want to show you something that I think is really cool, and I just can't help it, because that's just the way I am. So the product rule comes from the multivariable chain rule. Did you know that? Yeah, have you seen it before? Ah, well, here we go. Radio. So what if I had a function that was two other functions of x multiplied together? And then y is a function of f and g, and f and g are functions of x. Then dy on dx would be dy on df times df on dx plus dy on dg times dg on dx. And dy on df is g, because you keep the f constant and the g is like an x. And dy on dg is f. Ta-da! Product rule. The derivative of f times g is g times the derivative of f plus f times the derivative of g. Isn't that cool? Yay! It's stupid how simple that is. I mean, but there's a long way between, like if you didn't have the product rule already, then multivariable calculus might be a little bit intimidating. So yeah, but it's nice to know that everything's connected. Yeah, I remember someone showing to me this to me and going, but nothing happened. And later on, I thought it was cool. So there you go. The more maths, the more stuff you know, the less human, the more surprising things are, really. Okay, that's multivariable chain rule, and it can be a little weird when you've got something that's written as a function notation. So if you've got something that's like f of x and y is like g of x squared and y plus x, then it can be a bit confusing what the hell is going on with this, because g has two things that it's based on, but they don't have names. They're called x squared and y plus x. And it's not like f is equal to g, because g is a function of whatever's in these positions, and f is a function of the things inside the g, and so they're actually different things. It's not like before when we had this, where w was equal to a function of x, y, and z, and so w and f are the same thing. G isn't a function of x and y. It's a function of whatever these things are. And so most people find it easier to cope with this by saying let u be x squared and v be y plus x. And then we can say that f is g of u and v. And then we can go df on dx is, oh crap, we need to draw a diagram. F is a function of u and v, and u is a function of x, and v is a function of x and y. And so we can say df on dx is df on du times du on, that's a straight one, because there's only one variable there, and df on dv times dv on dx. And this one's curly because there's two choices here. Of course, I don't know what g is, and so I can't do any actual calculations, but I can do at least part of the calculation because I know that x, I can figure out this derivative, du on dx is 2x. And these are both 1. So I can do part of it. And this is one way of coping with that. And I should just warn you that if you're, yeah, how would we find df on du and df on dv here? We wouldn't unless someone told us more information about how the function g works. Yeah, so someone would have to tell you what the formula for g was, or they would have to tell you what the answer for g was at certain values of x and y, or certain values of u and v. And unhelpfully in the most recent assignment, the lecturer refers to dg on like the dg on du as g sub x, because they're just assuming that the name of the first variable is always x. So you're going to have to deal with that. But if you want to talk more about that, drop into the Maths Learning Centre and we can have a chat about the assignment question, but I don't want to do it in a revision seminar because I'm sure someone will get upset at me for putting stuff on YouTube about people's assignments. And of course it won't be relevant in 6 months' time. So, yeah. All right, how are people feeling about that multivariable chain rule? What about over there in Zoom land? All right, now that means I need to find my list. So, what's next? I do talk about series every semester and have done many times, but I can do again.
Can you go through proofs?
Good, that's what I wanted to do. So I have at least 2 people saying that. Actually, I'm just going to do it. As I've had people ask me this all semester anyway, so different people about talking about proofs. So these are the proofs. The proofs turn up in algebra, right? You don't have proofs in calculus so much in Maths 1B. Does that feel right? The old Maths 1B had proofs in both. It was fun, but they were different kinds, flavors, and they, yeah.
We have to do proofs in regards to subspaces, introduce proofs in regards to linear transformations, and proofs sometimes regarding like kernel or range and stuff. This is what we have.
And kernel and range are sort of part of linear transformations. I do know there's sometimes proofs that just straight up about matrices, maybe eigen things. Anyone online got thoughts about other sorts of topics that proofs could be about in Maths 1B? Cool. All right. If you think of something, just let me know when you think of it. So, right. So there's a problem with saying, how do you do a proof? In that every proof is different. And it's not like, and it's like, it would be like saying, how do you solve a maths equation? It's like, well, there's lots of different kinds of equations and they have different strategies. But proofs do have a few common strategies that I use that might be worth sharing. And I'll create some examples along the way that we can pull apart to see if we can find those strategies. And it might be easier to do that in reverse and to just do an example first. So, does anyone have a proof that they struggled with? Or that they thought was okay and then it turned out it wasn't, or anything? Because I can Google something as well, and that's fine. All right, I've got a classic one. Oh no, I'm wrong. Just a second. Oh yeah, it's going to be a combo of linear transformations and subspaces. It's probably straight out of the lectures, but I'm going to show you doing it live. Prove that the range of a linear transformation, F, which sends Rn to Rm, is a subspace of Rm. That's what we're going to do. So it's both linear transformations and subspaces. Okay. So I'm going to talk through my reasoning for coming up with this proof. And then we'll debrief afterwards to see if there's anything that we can glean for all proofs. And then I might do it again with another example. So I can't just tell you about strategies for proofs without doing one, so I hope that's okay. So all proofs have information that you're told and a goal that you're trying to achieve. So that's my first piece of advice. You need to figure out which is which. But before you do any of that, you need to understand what the words mean. So on the Maths Learning Centre wall, there's a big solving problems poster, and a lot of that is advice that works for proofs. So step 0 is to believe that you can do it, and to make sure you've got everything you need. It works well for exams, make sure you've got everything you need. But then step 1 is to understand the problem. And the big part of that for proofs is that you need to know the definitions of everything. Mathematicians have definitions for more than one purpose. One of them is so that they know what things mean and everyone has a common understanding of what the words mean. But they only give names to things that are worth talking about. And the other thing is that there are sometimes different choices for what the definition could have been. And they've chosen a definition specifically because it's the one that is the most useful for doing proofs. So it's not just that you must use definitions to do proofs, it's that the definition is designed to make proofs easier. Not easy, but easier. Yeah. So there are sometimes different choices they could have made. So we need to know what all the words mean in order to be able to do the proof. So we need to know what a linear transformation is. We need to know what a subspace is. We need to know what the range is. And we need to know what this notation is telling us. That seems to be all of the words that aren't, that are maths. I guess we need to know what RM is. And all the other words are that, the, of, is, and of. So I think we're okay. All right. So we need to know what they all are. And you don't necessarily write them down when you do the proof, but you do have to know. So I'm going to write them down. So the range is something that belongs to the linear transformation. You can see it's the range of a linear transformation. Oh, look, I'm actually telling you what of means in this context. So the range, this is telling you that the range doesn't exist by itself. It's a piece of information about a linear transformation. Okay? And the linear, this is just grammar at the moment. Linear transformation, this is called F, and this is a statement about the linear transformation as well. So it says it goes from Rn to Rm. So that means as a transformation, it takes things with n coordinates and spits out things with m coordinates. So it seems reasonable that whatever it spits out will be things with m coordinates, which is why it would be a subspace of Rm, because it's made of things that are in Rm. Okay, cool. Right. So a linear transformation needs a definition, and the definition of linear transformation, as far as I know, when what? It behaves, it preserves linear combinations. Oh, that should be like a K. That's a short version. You're supposed to have like for all U and V in Rn, and for all U, V in Rn, and K in R. But that's the definition. Now, there are other things that are true about linear transformations, and it's useful to think of them while you're pondering things. Other things that are true about linear transformations are that it's possible to write them using a matrix. And there are various other theorems that are related to them. But for the moment, it's the definition that we're going to have to use in the proof. So that's what I'm going to stick with at the moment. In fact, you should avoid talking about the matrix if it isn't mentioned. Yeah, linear transformation is a different thing from a matrix. It's just that they always have one, but you shouldn't talk about the matrix unless you're explicitly, it's mentioned already, usually. Never know. Okay, so that's what linear transformation is. And we know what it means that the U and the V are in Rn, and F of U is something that's in Rm. So just as a shortcut there, we know that when we write F of U, this is in Rn, and this answer is in Rm. So that's our understanding of what it means to this statement here means. And then being a subspace means that there's the three laws of subspaces. So W is a subspace when law 0, the 0 vector is in it. Law 1, if W is in big W and K is a real number, then KW is in big W as well. And law 2, if U and W are in big W, then U plus W is in big W. That's the definition of subspace. Now, there's other things about subspaces that we know to be true. We know that every subspace can be written as the span of something, and we know that every subspace is the solution to some homogeneous linear equations. They're things we know to be true about subspaces, and they have a basis, and lots of things are true about subspaces, but this is the definition. And so that's what we're going to do for the proof. And then I guess we need to know what the range means. So the range of F is, it's normally written like that, isn't it? Curly R, F, yep, which is the set of all outputs outputs. I'm just going to put that in inverted commas. That's what it is in my head. It's a set of all the outputs from the function. And as a set, it's the set of all things f of u such that u is in Rn, if it starts in Rn anyway. So it's all the answers that come out of the function, and the way to tell is to go, well, I'm going to have to do everything in Rn, and I'm going to find all the answers, and that's what the set is. Okay, so before I actually move on, I want people to tell me their thoughts about all of this at the moment. Something. Come on, you can do it. Yeah. So all these green things I wrote, it is green for those who can't tell. I say this because Nicholas, the other maths learning centre lecturer, is actually colourblind. So I would like somebody to say something. It can be a question, it can be a comment, but someone else other than me needs to speak right now. Mm-hmm.
But u is in Rn, shouldn't it be Rn?
Shouldn't it be Rm? Yep, okay. So, yeah, so the thing that goes in is in Rn. The thing that came out, which is what f of u is Rm. And yeah, so you have to run through all the inputs, and for every input, figure out what the output is.
So the range is technically the set of outputs such that the input actually.
Yeah. So I'm just going to repeat that for those who might not have heard it online. The range is the set of all the outputs such that the input actually exists, and that is completely true, and it was true back when we were doing ordinary functions. So when our functions weren't linear transformations and they just went from R to R, they actually went from a domain to R, and if you change the domain, it changes the range. So you go, the range is all the outputs as long as the inputs come from the domain. Yeah. And so they used to have things back in Maths 1A where they'd change the domain on you and the range would change. You might not have noticed it because you didn't talk about it in those words, but yeah. But, yeah, inverses and not one-to-one and that sort of thing. Or, you know, when they had functions where you put one function into another one and then there's another one and then the outputs of these don't naturally, like you get something that you're going to put under the square root, but the thing underneath it produces negative numbers, and so you have to change the domain so that it doesn't produce negative. Okay. So I've got a question from Declan. Do linear transformations preserve lengths and angles? When k is 0, the 0 vector is contained and fits in the subspace. How do you prove the other two properties? In fact, well done, Declan. We're going to run with that. So first answer is linear transformations almost always do not preserve vector lengths and angles. And in fact, when they do preserve lengths and angles, they are called orthogonal linear transformations, which is a whole other thing. And now we're going to do the proof, and so I can answer the rest of that. So now we know all that information. We're going to have a look at what the goal is now that we understand the bits of the problem. So the goal is to show that the range is a subspace. So the last thing we need to say in our proof is, therefore, the range of f is a subspace. That's the last thing we have to say, because that's the proof. The beginning of a proof usually starts with a suppose. That's just common. It's like a once upon a time for maths. No, do not write once upon a time, but it would be so cool if you did. If I was marking the exam, I would think that was fabulous. Once upon a time, there was a linear transformation. And the linear transformation went out walking one day for his porridge to cool. So we're going to have to make the statement that the range of f is a linear transformation, is a subspace, which means this W is the range of f that we're going to have in this definition, which means that we have to make all of these statements about the range. Now, this one is just the raw statement that the 0 is in the range, and Declan has provided a way to do that, and we'll deal with that. That's great. Excuse me. This one says if this is in W, then this happens. So when you want to prove a statement that says if then, in a proof it normally runs suppose therefore. And so I'm going to use the statement I want to construct sentences, long sentences with gaps in them, that's going to make my proof. So let f, which sends Rn to Rm, be a linear transformation. And I reckon since I don't really want to keep writing Rf over and over and over, I'm just going to call it W. Let W be the range of f. And then somewhere at the end of my proof, which I think is, because I'm writing in text, they're going to take me 2 pages. So somewhere over here at the end, I'm going to write, therefore, Rf is a subspace. I'm allowed to call it W, of course, because that's what I called it. But I have to finish with that. Great. Something in the middle. And I recommend in a written exam that if that's all you have time for, then say, the proof goes here, therefore this. Because then at the very least they know what that you know what the proof looks like. And if it makes a difference between pass and failing, they might give you half a mark, you never know. So just, you should always write something. Yeah, once upon a time. And they all lived happily ever after in a subspace. Okay, so we're going to have 3 parts to this proof. There's going to have to be, and I'm going to have to draw on my proof, I'm sorry, but there's going to have to be some sort of reasoning. And at the end of that, I have to conclude that the 0 vector is in W. There's no if here, so I don't start with any assumptions. I just have to say something. And then it says if W, all right, so I'm going to have to go suppose W is in big W and K is a real number. And then I'm going to have to do some working and conclude, therefore, KW is in big W as well. So I turned this, if little w is in big W and K is in R, working, therefore this. And there will have to be working here, I don't know what it is yet, but at least I know it has to be there. And then I'm also going to have to go, suppose U and W are both in big W, do some working, and go, therefore, U plus W is in big W. That's what my proof is going to have to look like. Again, you could do this, right? You can say working has to go in these spaces. And then they know you know what the definition of a subspace is. Right. So what are we going to put in these spaces? We have to convince ourselves that 0 is in the range. And the definition of being in the range is that you are f of u for something. Okay, so well, let's see. So we need f of something to be 0. And therefore 0 is in the range of f, right? Well, it's f of 0. And that's a little theorem about linear transformations, that f of the 0 vector is always a 0 vector. And as Declan said, it comes from the fact that if you have 0 as the scalar multiple, then that's how it goes. So you can prove that bit as well, but I think it's okay in Maths 1B to just do it. Unless the actual question is prove that f of 0 is 0. That would be a whole different thing. But I think, sorry? I have no idea if you'll get that question. We can do that one too. So that's fine. Okay. So we've given a reason. Probably don't even need this bit here, but it is useful to just point out that it's in the range. So maybe I'm going to waste time calling it W. Whatever. I could have just not called it W, but it felt right to me at the time. So suppose that little w is in big W and K is in R. So here's where this one's a bit trickier. And I'm going to go all the way back to my problem-solving chart, and it says, what do the words and symbols mean? And so I go, if I can't think of anything to do, I will look at what I've got and say, what does it mean? What does it mean for little w to be in big W? Well, it means it's f of something. So since w is in the range, it must be f of something for some u in Rn, because that's what it means to be in the range. You know what? I shouldn't have called it w. That was a bad move. I changed my mind. I'll just say consider the range. Because no one's going to remember that the w is the range, so I'm just going to call it. All right. This happens when you write proofs. Sometimes you change your mind. Okay, so that's what it means to be in there. And so we want to know whether k times w is in the range as well. So that means that k times w would have to be f of something. So we would like to do f of something, and for it to come out to be k times w. That's what we want, because then we can go, aha, therefore kw is in the range, because it's f of something. So we try and imagine what thing could it be, and so we're going to have to use some, we haven't used it, we're going to have to use the rules for what it means to be a linear transformation. Oh, this rule, that'll do. Just using it backwards, right? We'd like it to be, actually we'd like it to be k times f of u, wouldn't we? Because that's what w is. And so this rule, but backwards, would mean that we can do that. Cool. Should probably make the comment that ku is in Rn. Because technically you're only in the range if the thing you put in was in Rn. So that's the definition, isn't it? Yeah, we need to be in Rn, so we should mention it. I'm going to stop there. How are people feeling? And no, I'll do that in a minute. Okay. Now I'm going to have to do this. Same deal. What does it mean? This means that u must be f of something. Oh crap, I've already used u. I'll call it v. Oh crap, damn it. T? T? T feels weird to be a vector, but I know I'm committed now. For u and t in Rn, because it's in the range. Okay. So we want u plus v to be in w, and for u plus v to be in w, it must be f of something. So f of something equals u plus w, v plus w. And v is f of u, and w is f of t. Oh, and the rule for linear transformations, but backwards, is this. Okay, so f of u plus t is that. Yep, and note that u plus t is in Rn, and therefore this is in the range of f. And therefore, the range of f is a subspace, because I've done all three parts of a subspace proof. So, it is time for someone, either in the chat or in the room, or I mean, you can speak up with your voice if you're in the Zoom too, if you really want, to make a comment about something that I did here that you could reuse for other proofs. Yes?
Basically gone like I see a lot of analogies between this and writing an essay. And you basically use that as your paragraph, topic, sentences. Those 3 points that you need to address, and then you've got your conclusion.
The Writing Centre coordinator sits across the desk from me in my office, and she would be so happy to hear you say that. It is like writing an essay. You've got a topic, sentence, and you've got, in maths, the topic sentence comes at the end. It's the conclusion. But yeah, it's like writing an essay. You've got an introduction, you've got a conclusion, and you've got evidence in the middle. And yes, Cooper, we're going to do that. If-then statement can be turned into something like that. Okay. Anyone else want to say something?
If I do use the once upon a time in the exam, don't send me by it.
That'd be great. I don't get to mark the exams because I'm not part of the School of Maths. It's one of the advantages. One of the advantages of being the Maths Learning Centre lecturer, as opposed to a traditional lecturer, is I don't have to mark exams. Okay. It does mean I don't ever get to see the exam. So if everyone wants to come and do a debrief and let me know how it went, that'd be great. Okay. So why don't we do that little proof that f of 0 is 0, because it's a proof just as much as any other, and we can try and reuse some of the same strategies. So f, which kind of looks a bit like a p, sends Rn to Rm. F which sends Rn to Rm is a linear transformation. Prove that f of 0 is 0. Interestingly, this 0 is a vector in Rn, and this is a different 0 because it's in Rm. Look at us being sloppy. But we all know what we mean, so it's okay. This one has n coordinates, this one has m coordinates. So we want to make that proof. Declan already provided us with an idea for that. But before we do that, we need to know what linear transformation is. And we've got the rules for that. We wrote them down already. That's what it is. And that's the only technical terminology here, other than knowing what the 0 vector means, that these are 2 technically different 0 vectors. So we would like to prove that f of 0 is 0. So we need to probably start with f of 0 equals, and then write equals 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 0. Or maybe not, I don't know. So I have 2 approaches to do this, and I'm going to show you both because they're both correct. Okay, so way number 1. So I'm going to try and make this statement at the end of what I'm saying. So I'm going to do some sort of working and make the conclusion that f of 0 is 0. That's what I'm going to do. Okay. So traditionally, if you're going to prove something that's an equals, you usually start with one thing and finish with the other. And I'm going to give it a go. I don't know how many it's going to take. I'm going to guess 4, and if it's wrong, then I'll squeeze it in. Or if it's wrong in the other way, I'll cross one of the equal signs out. So, okay. So somehow I have to use one of these rules. And 0 times a vector is the 0 vector, so that seems reasonable. So this would be like f of 0 times some vector that isn't 0, or any vector at all. For any v in Rn. That'll do. Anytime you introduce a letter, you have to tell people what it means. Never allowed to introduce a letter that, unless you say what it is. So that's 0 times v. And so the 0 rule says that that should be f of v. You can bring the 0 out because that's the scalar multiple rule. And 0 times anything is 0. Done. Sorry? No, you do not need to prove that 0 times any vector is 0. That's one of the axioms of vector spaces. It would be like asking people to prove that 1 + 1 is 2.
So anytime there's an aspect of 0 doesn't mean
Yes. 0 times things not being 0 is possible. It's annoying, and we normally don't consider those things, but it's not impossible. What's really annoying is when you have two numbers that multiply to give 0, but neither of them is 0. That's annoying. Matrices do that, right? Two matrices, if you multiply them together, you can get the 0 matrix, even though neither of the original matrices are the 0 matrix. They just have lots of zeros, usually, but not all zeros. So, yeah.
You haven't satisfied the question. Do you have to do that as part of the proof?
So I'm going to repeat that. I haven't satisfied this one with the addition, and do I have to do that in the proof? No, I don't. I can use any part of the definition of linear transformation. I don't have to use all of it. If just part of it is enough, then that's okay.
Couldn't you have done the same thing? Let u equal to 0 vector, let v equal to 0 vector, and then just add.
And that was exactly way number 2 that I was thinking of, which was say, well, f of 0 is f of 0 plus 0, which is f of 0 plus f of 0. This is one way. I don't know if it's what you were thinking. And so I could subtract f of 0 from both parts of this equation and therefore get that. Just be even more explicit about it. Yeah, just so that everyone knew exactly what happened there. That's one way. You were going down a different path of how to write that. And I would like you to tell me what that is, because it's probably also correct.
I was just going to let you equal some other vector equal another 0 vector.
Like that?
Yeah.
And that would have produced this.
Yeah.
Okay. So would have the rest of the working would have been similar.
Yeah. Yeah.
And that would have been fine too. And that's directly using the way that we wrote the definition, and that sometimes is a little easier for people to follow. Yeah. This one I actually particularly like. I like the addition one because it only uses the fact that 0 is what you get when you subtract something from itself. So the only vector that you can add to itself and get the same answer that you started with is the 0 vector. Yeah. So cool. Right. Okay, so is there a strategy that I use there that people could reuse? Or a moral of the tale that you would like to take away with you? Write a story. Suppose and therefore. Yeah. Now you don't technically have to write them down, especially in an exam when you've got limited time, but you need to have them nearby. What's that? Yeah, so you don't ever have to give the number of the theorem. You can just say by a theorem. Unless it has a name, like the rank theorem, then you should say by the rank theorem. But if it's just numbered, nobody knows what the numbers are because that's just in your textbook. Yes? Yeah. Corollary? I thought you said corroboree. So different people have slightly different meanings for the different words that are used for those things. Everyone all mathematicians agree on what a theorem is. So a theorem is a thing that you prove to be true. Statement that has been proved or has been proven. I can't remember whether I'm supposed to be used the past perfect or what, but anyway, it's close enough. The perfect is always better and used by Peter Pan. So that's what a theorem is, any statement that has been proved, and it's usually something that you think is important enough to be called a theorem. So there are sort of other things which you could call theorems if you wanted to, but you don't think that they deserve such an important name. And so there are theorems that come before the theorem that you really want to be called the theorem, and they are called lemmas. Less important, used to prove the next thing.
So lemmas are less important.
For a mathematician to call something a lemma, that tells you that that mathematician thinks that lemma is less important than the thing they called a theorem.
Would that vary depending on the mathematician?
Yes, but in general, it is true.
Okay.
That's the psychology of writing mathematics. And then a corollary is less important, but it comes after the theorem that you used, that you just called a theorem. It can bring two theorems together, but it doesn't always. Sometimes it's your theorem, but applied to an extremely special circumstance. It's something you think is important to mention as a separate thing, but not important enough because it's just like, this is the big theorem, and then this is the next little thing that didn't take me much to prove, and here it is. Yep.
Yeah, so these lemmas and corollaries have to be proven or proved?
They still have to be proved. They are still theorems, they're just less important theorems. And a corollary in someone's paper could be a theorem in someone else's if they thought it was more important.
Yeah, but would the theorems and the corollaries and the lemmas change depending on what you're trying to prove?
Yeah.
So it's not set in stone.
Sorry?
So it's not set in stone.
No, it's not set in stone. But if something, if the entire mathematical community decides that it's important, then it will be a theorem forevermore.
Do they have like a board that does?
No, it's just all airy-fairy, and so it just sort of happens. I mean, you know, there are conferences and people present their stuff and people say, oh, there's a flaw with that and whatever. And who they get named after is a whole other thing. It's usually the person that proves them, but not always. Yeah.
So have like names.
Well, you know, like there's various Euler's theorems, and there's Fermat's last theorem. That's what it's called, which says that this only has whole number solutions for x, y, and z if n is 2 or 1, and doesn't for any others. It's called Fermat's last theorem because Fermat was the first person to have claimed to have proved it, but nobody knows if he actually did because he said, I have a wonderful proof of this, and my margin isn't big enough to contain it. Like he wrote it in the margin of a textbook. But Andrew Wiles was the person who actually proved it, but it's not called Wiles's theorem because of the history of this thing. I don't know whether Andrew Wiles feels upset about that or not.
Did he prove anything else that is your last year?
Oh, I'm sure there is. But like, yeah, anyway. So that's what those things are. So corollaries, theorems, and lemmas are all the same thing. They're just stuff that you proved. They're basically all the same thing. It's just that the word we use is describing where they fit in the story of the thing we're trying to prove. So my PhD, every chapter had a theorem, and there are all these lemmas that led up to the theorem. And possibly a corollary after the theorem, because we go, oh yeah, this theorem in this special case, isn't that nice? Well, yeah. Now, I did start late, so I can keep going if people want me to, but I can also just stop. Would you like me to do another proof? Or are you okay with what you've learned about proving? Apparently I'm supposed to tell you off for being mean, Declan. And that's forever immortalized now. Good thing you're not showing your face. Though I do cut everyone's faces out of the video anyway, even if they are showing. Okay. So what else? Well, all right. I think that's probably enough of the proofs. There is actually a whole seminar that I've done before called Proving Things in Algebra, which is a similar sort of idea. I do some stuff with eigenvalues as well. Yeah, but again, it's really based on the definition and attempting to arrange your proof to look like the definition of the thing you're trying to prove. Okay. Oh, that's because people were talking and I didn't notice. Okay. They're all on the Maths 1B page of the Maths Learning Centre website. So if you search for Maths Learning, University of Adelaide, resources, Maths 1B, it should do it. Okay, so what now? Do I talk? I'm going to ask people to choose between these things. I shall call this one A and this one B and this one C. If you're in the Zoom, you can put in the chat just A, B or C. And those in the room, you can tell me which of them you would prefer.
B.
Lots of B's in the chat. I think we're talking series. Okay. Now, here we go. Anything in particular about series? We've got here Taylor, binomial, divergence and convergence. That's pretty much the whole deal, as far as I know. I'm going to start with the thing that Josh was saying when he walked in, when I walked back in, which was that series are different from sequences. So mathematicians have two things that are related to each other. There are sequences, and they are things like, you know, just lists of numbers. For a mathematician, if they say sequence without qualifying it, they usually mean a sequence that goes forever.
Does that have to have a pattern?
No, it does not have to have a pattern. There could be no pattern whatsoever. For example, this sequence.
So you could like plot the x and y coordinates of like a weird pendulum, double pendulum thing, and that would be a sequence.
Yep. Yep, so you could, every second write down the x coordinate of your pendulum, and that would be a sequence. Or, you know, the digits of pi, which, as far as we can tell, don't have a pattern. It's certainly not, and if they do, it's certainly not a repeating one, because that would make it rational. But often they do, and to specify them, we normally give a formula to say how to figure out what term number n is, based on what n is. But this is short for 1, 2, 1 over 1, 1 over 2, 1 over 3, 1 over 4, etc. But the important thing about these sequences is they're just the numbers themselves. It's just a list. And when we talk about sequence converging, we talk about whether this list, if I follow it, if it gets close to something. And so for this last one, I can go, well, here's 0, here's 1, and I can go, well, there's the first one, and there's the second one, and there's the third one, and there's the fourth one, and there's the fifth one. And as I follow the sequence, it gets closer and closer to 0. So I just find where those numbers are, track where they go, and they all end up closer and closer to 0, and that's called sequence converges. Woohoo! And some sequences don't, and there are lots of ways. There are at least 2 ways to not converge. A sequence could just get bigger and bigger and bigger, like this one. And so it doesn't converge because it just keeps getting bigger. There's no one number it gets close to. Or it doesn't go anywhere in particular, like this one. It just keeps jumping around and never goes anywhere. Like this one. It'll always be somewhere between 0 and 9, but, you know, no particular place it goes. Okay. And lots of sequences that we care about converge to 0, but they're allowed to converge to other things. All right. Classic one is this one, which is this. That converges to 1. Sorry? So yeah, 4/5 is closer to 1 than 3/4, and 5/6 is closer to 1 than 4/5, because you're removing a smaller bit from the whole each time. Yeah, and so when we talk about what it converges to, we write the limit as n goes to infinity of n over n plus 1 is 1. So this is short. In words, you could say this sequence converges to 1. And so this word for limits, we use that for functions as well. But when we're talking sequences, it's always to infinity.
So it's like a derivative technically a sequence.
No, the derivative is not a sequence, because it's more, it's smooth. The way that you go to 0 is smoothly, as opposed to jumping from one spot to another. However, if you study real analysis in the future, you will discover that you can define everything as sequences if you want. So if you do have a sequence that does go to 0, you can just find the slope at each of those positions, and as long as that goes there, then it's fine. So don't discount it completely. Okay. So now we're talking about sequences. I really need to deal with some other things. And someone says, when is infinity over infinity 1 and when is infinity over infinity undefined? And the answer is, infinity over infinity isn't anything until you turn it into something that is not infinity over infinity.
Right, but if the n over itself, the biggest number is just 1.
Yeah, but infinity is not a number. Infinity is in this context, infinity is a place to be, and that place is a very large place. It's not like, you know, being at infinity is like saying I'm in Adelaide as opposed to I'm in the, whereas being at the number 57 is like saying I'm in the Horace Lamb Lecture Theatre. And so if I go infinity divided by infinity, I don't know which part of infinity is divided by which part of infinity. So it could be anything or nothing. So you have to turn it into something that isn't infinity over infinity, or you're not going to know what it is.
Wait, but is it infinity over infinity, it's only when it's a limit and the limit
Yes. So if the limit of the top is infinity and the limit of the bottom is infinity, then you can apply L'Hopital's rule if it was a continuous function. But that would turn it into a different limit that you would then calculate not using L'Hopital's rule. So the whole point of L'Hopital's rule is to turn your limit into something that isn't infinity over infinity anymore. That's what it's for. Yeah. So if you have a 0 over 0 or an infinity over infinity, you have to turn into something else. And in fact, there's only one limit law for fractions, only one limit law that tells you whether limits exist or not. And it goes like this: 0 divided by anything that isn't 0 is 0, right? Like that. And 0 divided by infinity is also 0, and that's okay. Not 0, but an actual number. Actual number divided by infinity is 0. So these are the ones we know for sure. And that says actual number. Not 0 divided by 0 is infinity. Possibly plus, possibly minus. I don't know which one it is. It would depend what the number was. Or if you like, does not exist. That's probably a bit more thing. And anything else, 0 over 0, infinity over infinity, infinity over 0, they all have to be manipulated until they're not that anymore. And once they are not that anymore, then you'll know what they are.
Wait, 0 or 0 is 1?
No.
It's just 0.
0, no, it could be anything or nothing. Yeah, because let's ask ourselves what division is. You could say if 12 divided by 3 is how many 3's fit into 12. How many zeros fit into 0? Oh, 2,000. Also true, 1. It could be anything. So that's why you can't do it. Yeah. And none of these are really anything anyway. It's not like you're doing 0 divided by 0 because it's never actually equal to that, because the limit never gets to wherever it's going. And so it's just close to that. So yeah. All right. So that's that. In general, I will tell you that this limit polynomial in n divided by another polynomial in n is always 1. Always. No matter what the polynomials are, if they're polynomials like n cubed plus 5n squared plus 7, whatever, and they're different ones, this limit will always be 1 every time. That's just the way it is. And the reason for that is there is reasons. Is because you divide by the biggest power you see, and you end up with a whole lot of 1 over n's and 1 over n squareds and 1 over n cubes. No, this limit's not always 1, sorry. Crap, I'm wrong. That's completely wrong. Something else is true. This one tends to come out to the leading coefficient on the top. Yeah, it's something else entirely. I was wrong. Ignore that completely. Something different. Sorry, everyone. Please don't, I hope no one turned it off like 3 seconds ago. This is not true. Something else is true about that, and I'll have to come back to that in a minute. It's this, like if you have an equals polynomial in n divided by polynomial in n, that, then this is always 1. Ratio test. So if your sequence is made of polynomials in n, and you do the limit of each one divided by the one after it, divided by the one before it, that limit will always be 1 every time. Ratio test will fail for something like that. Okay. So if you're running out of time, you can just write one when you do that. But I mean, you're supposed to do proper working. Yeah. Okay. Is that well answered, Declan? Yep. Yeah, no, I've tried scrolling. There's no more. Okay. So that's sequences. Sequences are lists of numbers. You can follow where the numbers are going and see if they're going anywhere, and that's the limit. Series is a whole other thing. So the act of taking a formula for a sequence. So just a second. This is a sequence. And if you whack this on it, now it's a series. This is a list of numbers, you know, A1, A2, and so on. This is just one number or nothing at all. It could be if there was an X in this formula here. But it's just one number. Like even if there's an X, each X represents one number. So this is one number, or possibly, you know, or nothing at all. No, well, this n is going to be replaced with all the numbers from 1 to infinity. So what this means is that we have to take an, replace it with all, you know, take this entire list and replace all those commas with plus signs, and whatever that adds up to, that is what this is. Right. Now, sure. And mathematicians have to be extremely careful about how to define what that one number is. And what they do is they make a new sequence, and I really mean sequence, which is the running total. So you've got A1 and A2 and A3 and A4 and A5 and A6 and A7. We can do A1, and then we can do A1 plus A2, and that will give me an answer. I shall call it S2. And we can do A1 plus A2 plus A3, which is S3, A1 plus A2 plus A3 plus A4, which is S4, and then S5. And so on. No, there's no plus there. This is the running total. I'm adding them up as I go and just keeping track of what the total was as I went. This is a sequence. That's a sequence of different answers for what the running total is so far. So I just want to do this importantly. So if I had the sequence 0. So if I had 0.1, 0.2, 0.3, 0.4, 0.5, they're my A's. Then the running total would be 0.1, 0.3, 0.6, because that's the running total so far, 1.0, 1.5, and so on. I'm adding up everything so far from the other sequence. This is a sequence as well. So you're adding more and more and more of the other sequence. And if you went forever to the end of this, that would be the one where you add up all the infinitely many of them. And so what mathematicians do is they define this to mean the limit of this new sequence that we made. So I call it the running total sequence. They call it the partial sums, I believe. Yeah. So that's the definition of what this means. It means make the running totals, see where that sequence goes, what happens now. This one will go to positive infinity. You know, it's the same as just adding up 1, 2, 3, 4, 5. I just divided everything by 10, so infinity divided by 10, it's still infinity. Yeah. Okay, Cool. So it's really important to keep in your head that a series is just a number, except with the small caveat that sometimes a series doesn't represent a number at all and it's just nothing. It's just a thing, a set of symbols I could write down, but that set of symbols in some sense is meaningless because there is no number to fit with that set of symbols. So that's the question we want to ask. So when we ask, does a series converge? We're asking, does this set of symbols represent a number? That's what we're asking. And the reason we're using the word converge here is we're thinking about the running totals getting closer and closer to something. That's why we use the word converge. Right. Right. So it cannot represent a number in two ways. One is that it could be like infinity, and the other one is it could never get to anywhere in particular, and when you do the running total, it flips and flops between different answers. Yeah. So that's the difference between this. 1 over n as a sequence converges to 0, because as n goes to infinity, it gets closer and closer to 0, 1 over n. But the sum of 1 over n equals 1 to infinity as a series does not converge. And that's because the running total just keeps getting bigger and bigger, and not in such a way that it gets close to something. It just... So the sequence, as I drew before, gets, you know, starts there, goes there, goes there, goes there, and so on. That's the sequence converging. The series converging is the running total. So we started at 1. I'm going to need more space here. We started at 1, and then we added on a half, and then we added on a third, and then we added on a quarter, and we got past 2, and then we added on a fifth. It does. Now, some sequences, the bit that you add on gets so small so quickly that there's a limit that you can't go past. But this one eventually goes up forever. But it gets there slower and slower and slower. If you want to get past 2, then you need like 5 terms. If you want to get past 3, then you need like 20 terms. If you want to get past 4, then you need like 50 terms. And it just takes longer and longer to get past the next number. But you can always do it if you want. That's the harmonic series. Whereas your geometric series will get, things will get small so fast that it will never get past anything. So if I had a half to the power of n, like that, the sequence, the sequence starts at a half, and then goes to a quarter, and then goes to an eighth, and then goes to a 16th, and it gets closer and closer to 0. So the limit as n goes to infinity over half power of n is 0. But the series, we have to do the running total. Trying to color code here. The series, first I'll add on a half, which was the first term. Then I'll add on a quarter and I'll get to there. Then I'll add on an eighth and I'll get to there. Then I'll add on a 16th and I'll get to there. And because I'm always adding half of what was left, I'll never get to 1. But what it does get to is it gets closer and closer to 1. Yeah. And we don't write it with a limit because all that limit stuff is contained by using the symbol infinity in that spot. This symbol is, where is this running total going to? It's going to 1. So the big question is, which series converge and which of them don't? Yeah. And that's the big question there. But before I do that, I do want to talk about just power series, because that's a whole special kind of series. So a power series, sometimes they start at 0, sometimes they start at 1, sometimes they start at 15. It doesn't matter. It makes a difference to the answer, but it doesn't make a difference to whether it converges or not. So, yeah, something like that. We'll deal with that special things. But a power series has sort of like no crap, it's not. Well, it does have a formula involving x, and n as well. And the idea is that given a specific x, you can sub that number in, and then it will be an ordinary series that only involves n. And you can decide, does that converge or not? And then for a different x, you can sub that in, and you can see if it converges or not. And so just as a proper example, it might be like, something like that. And the idea behind this is that you can pick different x's and you'll get different series. So if x is equal to 0, I get this. And that's a series, and it converges or doesn't converge. And if x equals, 4.5, then I'll get n equals 1 to infinity, n plus 1 over n squared, minus a half to the n. And if x equals 5, I'll get n equals 1 to infinity, n plus 1 over n squared, 0 to the n. And some of them will converge and some of them won't.
Is the point when you're putting your x in, going back, is that point to get another sort of theory to try and solve that square convergence?
That's what we're going to hope for. We're going to hope for a way to do it. But there is a shortcut that will tell you all the x's that will make it converge. And that is called the interval of convergence. So it's almost like, it would be nice to know what the actual number is that it produces. This one produces the answer 0 because they're all times by 0. And that one's great. And this one's going to converge. And this one's going to not converge. And different x's will give you different answers for converging or not. Yeah, I set it up that way. I don't know what number this produces, but I know it converges. This one's not going to converge because it's just going to keep getting bigger and bigger and bigger. Like, I do know that, at least. This bit's going to go to 0, but this bit's going to go extremely huge very fast. But this bit goes to infinity. And 0 times infinity could be anything. Because, that's 0 and infinity for you. Because it's never quite 0 times infinity. It's some very small number times some extremely large number. And very small times extremely large could be quite large. Or it could be 5. I don't know. So it's almost like we're drawing this graph that is, these are the values of x. And then it's not like we're putting numbers here. We're just going to say whether it converges or not. Like there's a yes and a no. It's like, this one didn't converge. This one did. No, this one did converge, didn't it? This one does converge. This one does. No. This one didn't. Oh, crap. Yes, no. This one didn't converge. This one did converge. This one did converge. And different x's, you would have to draw different answers for whether they converged or not. And so the ones that make it converge, these x's that make it converge, that's the interval of convergence. That's just random writing now. You can tell I'm getting tired. So a power series is like a function. It takes x's and it produces series as the answer. And sometimes those series converge and sometimes they don't. And if they converge, then the answer is a number. So you can think of it as a function, but when they don't converge, you're going to say, well, I'm just not going to include them in the domain of my function, and I'll be okay. And so the point of Taylor series is to take an existing function and rewrite it as a power series. Yeah. Because power series are sort of like polynomials. I mean, they go forever. That's annoying, but you know, close enough. Okay. All right. It's time for thoughts or questions before I say anything else. So how do you find the interval of convergence? That uses the ratio test. So I might as well just talk it out. This is in another seminar, and so I'm going to sort of do the quick version, but I'm not sure if I can. To tell if something converges. First thing you do is know if it's one of the classic series. And you just stare at it and go, that's one of the ones I recognize. Though most mathematicians would call it the known series, as opposed to classic, but classic sounds fun to me. So the classic series are this one, which is the harmonic series, and it diverges. And you're always allowed to say that. And I mean, they will not ask you to prove that it diverges in the exam. And the only way they could possibly ask that is if they did most of it for you and asked you to do a little bit of it. This is the alternating harmonic. And it doesn't matter whether that's an n plus 1 or an n there. And this one converges. And then there's anything that looks like this, which is a geometric series. And this one converges when x is less than 1.
What if it's bigger than 1? Does it not converge?
So if the size of x is less than 1, it converges. And the answer is going to be 1 over 1 minus x. And if the size of x is greater than or equal to 1, it diverges, which is the same as not converging.
Wouldn't it only be equal to 1 over 1 over x?
Oh yes, sorry. Has to start at 0 to be equal to this. Thank you, good move. So this tells us one of the strategies. If you can look at it and go, oh, it's mostly powers. Like if you can rewrite it so it's something to the power of n, where that something is just a number, then it's a geometric series. You can go, oh, that number's less than 1, converges. They're the classic ones. There is one more that comes later, which is this. And that is the Maclaurin series for e to the x. Yes, it's the Maclaurin series for e to the power of x. So when you do a Taylor series for e to the x, this is what you get. And this is equal to e to the x no matter what, and it converges always no matter what x is. And technically you're supposed to recognize the Taylor series for sine and cos as well. You can look them up another day. These are the classic series. If you see them, or if you can rewrite it so that it is those, then you're good. Then number 1 is the alternating series. No, just a second. What your lecturer calls the necessary condition for convergence. But online, if you Google it, it's usually called the divergence test elsewhere in the world. And I like to write it backwards So if something does converge, then the sequence that the series is made from has to converge to 0. So this is the actual statement in your notes. If n goes from 0 to infinity, converges, then the limit as n goes to infinity of the sequence that the thing is made from, not the running totals, but these bits as a sequence, that has to go to 0. But that doesn't tell you if it does go to 0, it doesn't tell you anything. So I like to think of it this way. If the limit as n goes to infinity of an is 0, is not 0, then this diverges. And if the limit as n goes to infinity of an is 0, then who the hell knows? So if you do that limit and it doesn't come to 0, then it's not going to converge. If it does come to 0, then it might or it might not. You still don't know.
Wait, did that say diverges or converges?
Diverges.
Okay. But if it equals, but if it's combined,
So if the limit of the individual terms is 0, then we don't know. But if the limit of the terms isn't 0, then we definitely know it diverges. Texters are running out. All right. Cool. And then there's the alternating series test, which goes you've got a series like this, and an is -1 to the n times some other thing that's positive. Has to have a -1 to the n. It has to flip back and forth between positive and negative. Even if it doesn't have a formula for it, it just has to be every second term is negative and every other term is positive. It could be. Bn could be, oh no, Bn couldn't be 0 because then it wouldn't be alternating. But then if every term was 0, you wouldn't care because you'd just be adding up zeros. So. So there's 3 things that have to be true. You have to have this, it has to be alternating. No, only 2 things. Oh yeah, and the limit as n goes to infinity of Bn has to be 0 because otherwise it won't converge at all because that's the previous test. The Bn has to be decreasing, meaning that each one of them is smaller than the one before it. So Bn is greater than Bn plus 1, which is greater than Bn plus 2, forever. And then it converges. If this isn't true, then it will definitely diverge. And if it has to be alternating series anyway, if you have alternating series and this and it's not decreasing, then it may or may not converge. I'm pretty sure. Could be wrong. I'm not sure about in general, if it doesn't fit the thing, you don't know. Yeah. And then finally, there's the ratio test. So you know how this one, the terms have to be decreasing? The ratio test is similar, but instead of just saying that it's bigger than that, if you divide 2 things and the answer is less than 1, then that means that the bottom one is bigger than the top one. And so the ratio test goes that you've got a series, doesn't matter where it starts, and you calculate this, or is it the other way around? No, it's each one divided by the one before it. Yeah. You calculate this, and then you do the limit of that as n goes to infinity and it will either produce an answer or it won't. And there's three options. It might produce the answer, an answer that's greater than 1, in which case it diverges. Or it might produce no answer at all, in which case it diverges as well. It might produce an answer less than 1, in which case it converges. Or it might produce the answer equals 1, in which case we have no idea, and it could be anything. Yeah. And that's the ratio test. And it's particularly useful for series that have powers in them and factorials in them. Cool. And again, it doesn't really matter where this starts for using the ratio test because you're looking towards infinity anyway. So if there's no pattern in particular for the first 100 terms and after that there's a pattern, just use the pattern that's at the end. Okay. The ratio test is how you decide about power series. Because when the power series has got like an x to the power of n in it, and so when you go x to the power of n plus 1 divided by x to the n, they cancel, you're just left with an x. And the other crap has to turn into something, but you'll always be left with just an x. Oh no, you've got to do the absolute value of it, sorry. That's important too. So they're really good for power series. And what it will do is it will guarantee you to have this zone where it definitely, it'll tell you this bit, and it'll say it definitely converges in this bit here, because this was my yes converge and no it doesn't converge. But it won't tell you anything about what happens at these spots, because they're the spots where the ratio test comes out to be equal to 1. And so the only way to tell them is to come back to usually your, oh, I missed one of the classic series. Always forget the P series. P is greater than 1 or equal to 1, it converges. No, it has to be strictly greater than. And if P is less than 1, it diverges. It's important to point out that this one is different to this one, in that this one the n is in the power, this one the n is in the base. And in this one the x is a constant, and this one the p is the power is the exponent is a constant. So that's what makes them different. Yeah. Converges. Because it makes sense that it would be more likely to converge if the bottom was bigger. And so n to the power of big number would be a big thing. That's how I remember it. Small, yeah. If the bottom's small, then it's not going to 0 fast enough for the running total to just keep getting bigger and bigger. So the classic is 1 over root n, because you go, oh, that's n to the power of a half, and the half is less than 1, and so therefore it diverges. Yeah. Cool. So that's all of that. I'm going to have to stop in a moment because I'm wearing out, and we're all wearing out. But I will answer Jad's question, which is how do you shift the index over? So there's a classic problem that goes, and make it 11 because that's fun. Okay, so I have 5 times 3 to the n over 5 to the power of 2n plus 11. This has enough powers in it for it to probably be a geometric series, if I fiddle with it enough. So the first thing I'm going to do is I'm going to do this. And note that this 5 will cancel with that a little bit because they're all powers of 5. So that's okay. Divide this by 5, divide that by 5. And in fact, that 5 to the 10 is annoying, so I probably should have moved it out of the way in the first place. Okay. I wrote that step. I would have skipped that step if I was in an exam. Or maybe I wouldn't have, because I would have been really freaked out about me being right. Okay. And I'm getting to the thing that Jad actually asked. I just can't help but do this problem now. And I notice that 5 to the 2n is the same as 5 to the n squared, or 5 squared to the n. I should have done this working out without the sum sign. I should have just done the algebra, shouldn't I? And then put it back in later so I wouldn't have to write a million sum signs. Oh well, too late now. There we are. We are finally at the stage where we can tell that this is a geometric series. Geometric series converges. Woohoo! But if you want to know what it converges to, geometric series only have rules. The formula for geometric series only works if you start at 0. So you've got two choices. One is to think, well, if it had started at 0, I'm missing the one when n equals 0 and the one when n equals 1 and the one when n equals 2. So there my two, there's a choice. I could say that it's the sum from n equals 0 to infinity of 3 over 25 to the n. But I'm missing, I am missing the one when n equals 0. And I'm missing the one where n equals 1. And I'm missing the one where n equals 2. That's one way of dealing with it. The other way of dealing with it is to note that that this n is just a number that I'm going to replace with numbers later, so I can change the way the formula works. And so I would really like this to be starting at n equals 0. And if I did start at n equals 0, that would be different to what I've got here. This one starts at 3. So what I can do is I can put an n plus 3 here, so that when n is 0, I still start with the power being 3. And then when n is 1, I still got the next power being 4. So I can make this 0 by changing where the n is, adding something so that it still works out to be the same list of numbers that I'm adding up together. And the classic way of thinking about it is to go, I've subtracted something from here, so I have to add something here. Here you go. And if you do differential equations 2 either straight or for engineers, this will come back, this act. And this one's a little easier to work with than this. Because now I can do this. And pull that number out the front. And now this formula is n 0 to infinity x to the n, so I can use the formula for the geometric series. And it's horrible, but it's the answer. It's a very small number because of this 5 to the power of 10 here. I really don't like fractions within fractions, and I have a desire to make that go away. So what I'm going to do is I'm going to, if I multiply this by 25, that'll make the 25 on the bottom go away. So if I multiply this, and I can't multiply the bottom of a fraction by 25 without doing the top as well, so I'll get 25, I'll get that. And this I can cope with. I'm okay with that. I would probably expect someone in an exam, if they gave this, to give numbers that cancelled out nicely. This is my favourite fraction trick of all time. I love it. All right. Well, there we go. Does anyone want to talk about what just happened there? All right. In that case, I'm going to stop. Thank you so much for bearing with me while the technology was crap, and being here and asking excellent questions and making good comments. What will happen over here? Oh, right. Minus crap. So this bit will become that, and then you'll have to subtract these three pieces separately. Now, if you really want to simplify the fractions, you can, but I wouldn't if I were you. Thank you, everyone. I'm going to stop everything yes. Good luck with your exam. No, you don't need luck. I wish you calm nerves, helpful technology, and clear thinking in your exam.